of the day on multi-party computation. We have the first speaker up he's going to present on how to obfuscate MPC inputs. The speaker is Ian McCoy. Take it away.
Oh, okay, great. So hello, everybody. I'm presenting a joint work with my two co-authors, Mike Roselick and Jiayu Xu, on, as you said, how to obfuscate MPC inputs. So let's start off with something we're all familiar with, just two-party computation. So in this setting, we have two parties, Alice and Bob. They both have their own inputs, and they want to jointly compute some function on their inputs. Now, of course, their inputs are private, so we want each party to learn the minimal amounts of information about the others. In this case, Bob learns nothing from the interaction, and Alice learns the output of the function on their joint inputs. But of course, Bob spent a lot of time finding his inputs, and he's worried about server compromise. He's provided this service, but he's worried about somebody compromising his server and learning his input. So instead of inputting his X directly into the protocol, he inputs some encoding of X that prevents the adversary from immediately learning his input. So what does this look like for something simple like a point function? Well, in this case, the online steps are the exact same as we'd see in 2PC. But on compromise, the adversary only learns Oracle access to the function computed by the 2PC interaction. And as Bob only inputs this encoding of his X into the protocol, then an adversary, upon compromising Bob's service, can always evaluate the online protocol in their head using Bob's encoding to gain access, Oracle access to this equality oracle. So indeed, this is the smallest amount of information that we are able to leak upon compromise of Bob's service. And of course, we want it so that access to this equality oracle can only be gained upon after compromising Bob's service. Well, generally speaking, what we call input obfuscated 2PC is exactly what we've seen earlier, except for instead of having the specific case of an equality oracle upon compromise, we have access to this residual oracle F, which is the function computed in the interaction, primed on Bob's input. So what we show, and what we hope to show you today, is that you can achieve this strong notion of input obfuscated 2PC for any function which has a VBB or a virtual black box obfuscation in either the random oracle model or in the generic group model. And we achieve this by replacing the normally non-interactive oracle queries to the random oracle and to the generic group with an interactive protocol run between Alice and Bob. So what exactly is VBB? Well, in a nutshell, it consists of two steps. An obfuscation step where we compute some obfuscation of a function after interaction with possibly interaction with some oracle, and an obfuscation step where we're able to evaluate an obfuscation on some secondary input. And of course, this obfuscation that we provide can be simulated with only oracle access to the underlying function. So back to what we were talking about earlier with point functions. 2PC for using BBB for a point function looks what we see here. Basically, in the obfuscation step, Bob sends his input to the random oracle and gets back a handle, and this handle represents the obfuscation. He sends this obfuscation to Alice, who then queries the random oracle she has. All of this, of course, done locally, and then just does string comparison against the handle she received from Bob and the handle she received from her random oracle query. Now, what we want is this random oracle query that Alice makes to be interactive. We want her forced to interact with Bob whenever she wants to make this query. Well, as it turns out, we know how to construct this already. Drecke et al. Show that it's possible to construct such an interactive random oracle in a oblivious pseudorandom function. In this case, Bob inputs a key to the oblivious pseudorandom function, and Alice only learns interactively the output of the query. And of course, Drecke et al. Show that this achieves the same programmability and observability properties required from a random oracle. And as we saw earlier, here's our point function. And what we want to do is we want to apply this intuitive compiler. Basically, what we do is we replace the non-interactive Oracle queries to the random Oracle with now interactive queries to Bob's OPRF. And indeed, this achieves input obfuscated 2PC. As upon compromise of Bob's service, the adversary learns Bob's input K, which now allows them to compute the interactive random Oracle locally. But since Bob only stores a VBB obfuscation, the adversary only gains access to this obfuscation, which is indeed Oracle access to this residual function. So in the general case, just as we saw with the point function, we have two steps for a VBB obfuscation, obfuscation interacting with the random Oracle and evaluation interacting with the random Oracle. And all that we do is we replace the random Oracle queries with now interactive random Oracle queries, aka we replace it with the OPRF. Now, why isn't this trivial? Why can't we just run all of these steps in 2PC? Well, the thing is this obfuscation requires interaction with an idealized object. And this idealized object, the random Oracle, is exponential in size. And so we can't just run it generically inside of 2PC. Well, if we can also construct such an interactive version of an idealized primitive in other models, maybe we can achieve IO2PC in those models, such as the generic graded encodings model or the generic group model. Well, as it turns out, we can at least achieve this in the generic group model. So we just, in the last session, I believe, we learned about generic groups, but just really fast, just as a random Oracle is an idealized version of a hash function, a generic group is an idealized version of a mathematical group. And on top of multiplication, since we consider generic groups for uniform encodings of the group elements, we also provide an identity test, which allows an interactor to learn if their given element is an identity element. So what we do is we, just as an OPRF is an interactive version of a random Oracle, we construct an interactive version of a generic group. In this case, Bob holds a key, which is a pseudo-random permutation key, along with a new generator in the public generic group. Since we're compiling from a public generic group to an interactive protocol, we still have access to this public generic group. So we sample a new generator for that group and a key to a pseudo-random permutation. Then elements in our new private or interactive generic group are masked elements in the public group. In this case, this M here, this G to the M, is a multiplicative mask on the underlying elements. And then we store the mask under a pseudo-random permutation keyed on Bob's input. In this case, multiplication, although this looks a bit odd at first glance, is actually exactly what we'd expect. We multiply, so the second elements being just group elements in the public group, we just multiply them together and provide a fresh mask. And then, since we want to keep everything consistent, we store that fresh mask under the pseudo-random permutation, just as we did in the base elements. And one thing, if you guys remember, we still want everything to be interactive. Now, the second part can be computed in the public group, so non-interactively. Everything here can be computed locally. But in order to store the new fresh mask under pseudo-random permutation, we require access to Bob's key. And so Alice and Bob can run, they can run a reintegration of the mask into the pseudo-random permutation interactively using generic 2PC. Then finally, we have to consider the case of the identity test, since we provide two oracles to our generic group. And then the second one, the identity test, this is the case where X is just equal to 0, right? So looking at our group elements, we have G hat to the 0 is the identity element. And so we are interested in if Alice's element is just G to the M for whatever M is stored within the pseudo-random permutation. Well, this equality can be done locally. This equality check can be done locally in the public group. So what we do is we have it so that Alice only learns a blinding, in this case, a exponential blinding of her element that she holds, and she can now compare that to g to the blinded m that she gets from Bob. This step is done interactively, and so can't be computed by Alice locally. And as we saw earlier, in the random oracle case for BBB obfuscation, we just wanted to replace the random oracle with a keyed and interactive version of the random oracle. Well, in this case, we do the exact same thing. We replace the GGM queries, the multiplication query and the identity test query, with interactive versions inside a personalized generic group. And indeed, this allows us to achieve input obfuscated 2PC in the generic group model. Now, for what we've done in our paper, and I really suggest reading it because it's quite a bit longer than the proceedings version. We introduce the idea of and study of input obfuscation for 2PC. We also provide a compiler from virtual black box obfuscation in the generic group and random oracle models to IO2PC in those models. And to construct the latter, we construct an interactive version of the generic group, which is analogous to an oblivious pseudorandom function to a random oracle. And we provide explicit IO2PC protocols for point functions and for hyperplane membership using our compiler. And for an interesting open question we pose, we believe that an interactive version of a generic graded encodings is possible. And with that in hand, using this general technique, you would be able to construct IO2PC for all of P. Thank you.
Thank you. Questions? Okay, if not, I just had a quick question while the next speaker sets up. I just wanted to clarify, what do you mean by generic grading encodings? Like, what would it mean here in the conjecture?
Yeah, so inside the generic graded encodings model, if we're able to construct an interactive version of a generic graded encodings, then we could, since we have BBB for all P in the generic graded encodings model, we just replace the generic graded encodings queries with interactive versions, which would then construct, since we have BBB and we compile BBB into IL2PC, we get IL2PC for everything in P in the generic graded encodings model, if that answers your question.
Yeah, that answers. Thank you. Let's thank Ian once again. So our next talk is on fully secure MPC with minimal trust, and Divya Ravi would be giving the talk.
Everyone. So this talk is on fully secure MPC with minimal trust, and it's based on a joint work with Yuval Ishai, Arpita Patra, Shikhar Patranabis, and Aksharam Srinivasan. So let me quickly begin with what secure multi-party computation or MPC means. Suppose you have n mutually distrusting parties out of which T are corrupt, and the goal is that they want to compute some combined function on their private inputs. MPC gives them a way to do so while ensuring that they get the correct output and that nothing beyond the function output is revealed. Now, you can have different types of MPC protocols with different types of guarantees, and two of the strongest guarantees are fairness and full security. So fair protocols are fair in the sense that if the adversary gets the output, then so do the honest parties, but it may happen that in such protocols, nobody gets the output. But there is a stronger guarantee called the full security or guaranteed output delivery, in which no matter what the adversary does, he cannot prevent the honest parties from obtaining the output. So if you're designing protocols, you will try to get these strong guarantees, but unfortunately, there is a classic impossibility result by cleave, which said that you cannot get these guarantees if you assume that the adversary is corrupting a majority of the parties. So now how do you bypass this if you still want to get these guarantees? So one obvious option is that you assume an honest majority setting. And in fact, in such a setting, you can get these guarantees, and it has been very well explored in the MPC literature. And there is also another option, which has been relatively less explored, in which you continue to be in the dishonest majority setting, but still you get these guarantees by assuming some sort of external help. So you can imagine such protocols as being like a regular MPC protocol, except that occasionally from time to time, you have access to this genie who is doing some computation for you and then helping you get these strong guarantees. So let's try to understand how to model this trusted party or this external help. So in our work, we mainly focused on two main dimensions. One is about what kind of computation we make this trusted party do, because we may want to pose some restrictions on the kind of wishes that the genie is granting us. And the other dimension was that how many times do we use this trusted party? How many wishes are we getting? So let's analyze the existing solutions based on these two dimensions. So one trivial way to get full security would be that you just make the genie compute the function itself directly. And this would need just one call because all of the parties can simply send their inputs to the genie. That would be counted as one call who computes the function and gives you the output back. So this is great in terms of the number of calls because one is just the minimum that you can use. But if your circuit is large, then maybe you don't want to do such type of heavy computation using this external TP. Next, there was this work by Ishai and others in 2012, and they managed to get full security by making the TP do some small and lightweight work. And by this, I mean that it was independent of the function being computed. So that's great. But on the downside, this was using the trusted party n number of times, where n is your number of parties. So this is something that you want to avoid if you're in a setting where the number of parties is large. And in the same paper, they also had a solution with one call, that is the optimal number of calls. But here, the amount of work that they were making the trusted party do was exponential in the number of parties. So maybe you also want to avoid this if your number of parties is large. So the ideal goal would be if you could get full security with just one single call to a small TP. And by small, I mean that the complexity is polynomial in the number of parties and the security parameter. And in particular, it's independent of the function that you're trying to compute. So now if you imagine that this trusted party is going to be realized by some cloud service provider who is charging you some fees for a computation, or you're going to use instances of a large scale honest majority MPC to do this functionality related to the external help, then it makes sense that the TP is an expensive resource and you want to try to minimize how much you use it in terms of how many times you're using it and what type of computation you're making it do. So that's why we wanted to achieve this goal. So again, our goal is to try to get full security with one call to a small TP. But we started on a very negative note because for a large class of protocols, we showed that, in fact, you have to make the TP do work that is exponential in the number of parties if your decoder is universal. So what I mean by the decoder being universal is that once you invoke the TP, you're just allowed to invoke it one time and you get a response, then the kind of computation that you're doing to derive the output from this response, if we assume that it's independent of the function to be computed, then we showed that exponential size is inherent. And we were particularly interested in this class because the one call solution of Isha and others was fitting into these class of protocols. So what we are saying is that since they are having a universal decoder, they could not have done better than making the TP do work exponential in the number of parties. And this negative results holds irrespective of the computational assumptions or the setup. So now if you want to any hope of a positive result, then you have to allow this decoding to depend on the function. So that's exactly what we do. We allow the function dependent decoding. But here we got another negative result, which showed that you cannot get information theoretic security in the plain model. So this means that we have to either switch to the computational setting, or we could consider the information theoretic setting with setup. And in the computational setting, we finally had a positive result in which we showed that you can get full security by making just a single call to a small TP. And this is a very simple construction based on functional encryption. And this other direction is still open. So we still don't know what happens in the information theoretic setting with setup. So for the rest of the talk, I will just elaborate on the positive result based on functional encryption. But before that, let me recap the syntax of a functional encryption scheme. So first, you have the setup algorithm, which sets up your master public key and the master secret key. Then you have the key generation that takes in the master secret key and the function f, and it would give you a functional secret key, say skf. And encryption takes in the master public key and your input plain text X, and it gives you the ciphertext C. And decryption would take in this ciphertext and this functional secret key, and it would give you an output. And if everything is good, then the output is nothing but the function f evaluated on this plain text input X. So this is just a recap of what a functional encryption scheme looks like. So now let's see our fully secure MPC with one call to a small TP. So what we do in this construction is that first we run an instance of an MPC protocol with identifiable abort. Now, this is the best type of guarantee that you can get in a dishonest majority setting. And the guarantee is that it may happen that the honest parties don't get the output, but in such a case, they would identify at least one corrupt cheater. So we use an instance of this, but we don't use it to compute the original function, because if we used it to compute the original function, then you would violate fairness because the adversary would get the output and not the honest people. So instead of using it to compute F, we use it to set up these keys for our functional encryption scheme. So this outputs the master public key and the functional secret key. The idea is that if a run of this results in a bot, then you eliminate the cheater and you keep rerunning this until it is successful. At some point, all the cheaters will be eliminated and you're sure that it will be successful. So the parties do this until it's successful, and then they move on to the next phase. So in the next phase, what the parties would do is they would simply send this master public key that was the output of the MPC and their inputs to this genie. Now note that the corrupt person can, of course, misbehave. For example, this adversary is sending the correct master public key on behalf of P2, but on behalf of P4, it's sending a different one. But from the point of view of the genie, he has no idea about who is lying or who is honest, because we are in the dishonest majority setting. So for all the genie knows, the red master public key could be the correct one, and maybe the first three are corrupt. So the genie cannot really identify who is good and who is bad. The best thing that he can do is he can just try to create a partition based on whoever is sending him consistent information. So that's exactly what the genie does, that he just creates a partition with a set of people who sent him the blue master public key and the set of people sending him the red one. So for the set of people sending him the blue one, he would prepare a ciphertext using this master public key, and he will use the inputs just sent by them and a default input by the fourth one. And similarly, he will create another ciphertext using the red master public key, but in this case, he would use only P4's input, and then he would use default inputs for the others. And now he just simply returns these ciphertexts to the relevant parties. The point here is that we are sure that the honest parties will always be in the same set because they would be sending consistent information to the genie. So now as an honest party, if I get a ciphertext, from the genie, I just decode it using my functional secret key, and I get this particular output. Now, of course, the adversary can have corrupt parties in different sets, so he can get multiple outputs, but note that all the outputs would be, except the one in which was belonging to the set of honest people, all the others would be on default inputs of the honest parties. That's why it does not violate security. So it's clear that this construction is using just one call, but let's analyze what work we are making this genie do. So we mainly made it compute these ciphertexts. So now the size of these ciphertexts would depend on the type of FE scheme that you're considering. So if you take one that is based on sub-exponential LWE, then the complexity would be polynomial in the number of parties and the security parameter, but it would depend on the depth of the circuit. But if you wanted it to be ideally small, not depend on the circuit at all, then you could use the functional encryption scheme that is based on IO. So this is our construction, and note that this is not violating our negative result because the decoding that the parties are doing to derive the output from the response of the Gini is depending on the function. That's why it's not violating our negative result. So, so in the last construction, we are just sending the inputs on clear to the Gini, and this is maybe something that people are not comfortable with, and you want to try to assume that the TP is at least semi-honest, not completely honest. So that's why we looked at these other models, which in which the adversary could corrupt a majority of the parties actively, and also it could corrupt the TP in a semi-honest manner. So we refer to this as the colluding model. But here we showed that you cannot circumvent Cleve's impossibility and that fairness continues to remain impossible. We also considered this other next best option of the non-colluding model in which it can perform only one type of these two corruptions. And here we found that whatever was the previous construction, you could make some modifications to it to get security against a semi-honest TP. So now you will not be sending your inputs on clear to the TP, but doing something slightly different to get security against a semi-honest TP. So this is basically a summary of our results. And I already mentioned one of the open questions, but there are plenty of future directions. Like we don't know if we need something like IO for this ideal small solution. And also we restricted ourselves to one call, and the work of Isha and others was N call, but there's nothing known in between. Maybe there are much more simple solutions based on simpler assumptions if we say, consider two calls instead of one call or anything in between 1 to N. So that's basically it. Thank you.
Thank you. Does anyone have questions?
We think it would make sense to compile this with like a honest majority protocol, where the honest majority protocol runs this this trusted party, and then you have a very the honest majority is only for the very limited functionality, and the dishonest majority for the rest.
So, I mean, the way that we were trying to think that if it's a large scale one, then maybe you're assuming that it's honest majority, but are you saying that the functionality is in a way that you can do it, in, you can get fairness even in that, or maybe I'm not getting your question. So whatever the TP is doing, we want to realize it using just for those type of that part of the computation. We may consider like involve more parties. We consider like more number of parties so that we are now hoping to have honest majority in the bigger set. And then we are realizing it through that. But are you suggesting something different?
I might not be understanding it
Okay, then
correctly.
try it. Otherwise we can take
No,
it offline.
no, I think it's better if we take it offline. I think this will take too long.
Okay, let's thank Divya again.
Thank you.
All right, Alex. Yeah. Hello.
Okay, so the next talk is on statistical security in two-party computation revisited, given by Pratik Sarkar.
Hi, everyone. So my name is Pratik. Today, I'm going to talk about statistical security in the two-party setting. This is a joint work with Sai Krishna Badrinarayanan from SNAP and Shikhar Patranabis from IBM Research India. So today we are going to talk about two-party computation. So here there are two parties who have private inputs X and Y, and they want to compute a function F. So for that, they run a protocol pi on their function. And the correctness says that the protocol output is same as the function output. And security says that the protocol output does not leak anything about X and Y beyond the protocol output. And we designate the right-hand side party as the receiver and the left-hand side party as the sender. And in our setting, If one party gets the output, we consider it's a receiver who gets the output. And if both parties get the output, we consider that is the receiver who receives the output first. And in this talk, we are going to focus on two-party computation in the plain model. There are no setup assumptions. And we are going to consider one message exchange model where in every round, only one party is supposed to send a message. So we do not consider simultaneous messaging. So our results are in the non-simultaneous messaging model. So in this talk, we are going to focus on round optimal 2PC in the plain model, where one of the parties is computationally unbounded. We consider security against malicious corruptions, and we consider polytime black box simulation-based security. So why do we care about round complexity? Because like fewer rounds impose less network latency. So it's always ideal to have like the round optimal protocols. And also round optimal protocols have other useful applications in cryptography. So let's revisit some of the lower bounds in the 2PC domain. So it's known by, due to the seminal work by Katz and Ostrovsky, that 4 rounds are necessary if only one party wishes to get the output. And 5 rounds are necessary if both parties wish to get the output. Remember that this is the non-simultaneous message exchange model. There's also another work by Katz, which shows that 5 rounds are necessary for zero knowledge proofs for NP statements with black box simulation. So if we consider this in our setting, this means that the unbounded prover is the information theoretic sender, and the computational verified is the computational receiver in our setting. So this kind of rules out round, 4 rounds protocol when the sender is computationally unbounded. So this is like the summary of the lower bounds. That means we cannot get a protocol which is like 4 rounds. Which is like 5 rounds where both parties get the output. So 4 rounds are necessary when the receiver learns the output. 5 rounds are necessary when both parties receive the output. And 5 rounds are also necessary when the sender is computationally unbounded. So then what can we achieve in 4 rounds? So the optimal 2PC that we can achieve in 4 rounds is against a computationally unbounded receiver and computationally bounded sender. So this was studied by the work by Khurana and Mugis in TCC 2020 paper. And they coined this term as one-sided statistical security. So we are going to focus on this setting. So now let's see the results in the one-sided statistically secure 2PC. So what do we know about this? So the paper by the KM20 paper, they obtained a protocol which is round optimal. And they constructed this protocol from basically this ingredient called 2-round statistically sender private OT. This means that it's a 2-round OT protocol where the receiver is statistically, receiver is computationally unbounded and the sender is computationally bounded. And here the sender's message, one of the sender's message is statistically hidden from a corrupt receiver, and the receiver choice bit is computationally hidden from a sender. So this is like a 2-round SSP OT. And they instantiate their compiler by instantiating the underlying 2-round SSP OT from decisional hardness assumptions like DDH, QR, DCR, LWE, decisional C-site, and recently from LPN plus de-randomization style assumptions. But the problem is we want to instantiate this compiler from obtain this compiler from computational assumptions like CDH, but we do not know 2-round SSP OT constructions from CDH. So our work basically constructs a new generic compiler for one-sided statistically secure 2PC. And we obtain this result from weaker ingredients, mainly a 3-round elementary OT, which with its statistical receiver privacy and non-interactive commitment scheme. So what we do is we relax the round requirement from 2 to 3. And this kind of allows us to obtain new instantiations from computational hardness assumptions. Mainly, we obtain the first instantiation from CDH and the first instantiation of from reciprocal C-site, which is weaker than decisional C-site. So these are like isogeny assumptions. And we also re-obtain the result by KM20 by showing that 2-round SSPOT actually implies our weaker ingredients. You can construct our ingredients from 2-round SSPOT. So we re-obtain the results. So now let me briefly define this elementary OT protocol. So it's a 3-round OT protocol where the sender sends the first message of the OT protocol. The sender has 2 input messages x0, x1, and the receiver has choice bit gamma. And the sender is computationally unbounded. while the receiver is computationally bounded. So it's like the role has switched. And now the properties that we need from this EOT protocol is that the receiver outputs X gamma, and we need statistical receiver privacy. That is, gamma is statistically hidden from a computationally unbounded sender. And we need this elementary sender privacy, which is the computationally bounded receiver cannot compute both X0 and X1. So this is the elementary sender privacy property. So using the EOT with SRP property, we are gonna check out how do we build this compiler for one-sided statistical 2PC. So I'm not going to go into the compiler construction, but I'm just gonna briefly highlight the result by KM20 and what changes we make in it. So they obtain this round optimal one-sided statistical secure 2PC from 4 primitives. So the first primitive is a 2-round statistically sender private conditional disclosure of secrets. Then they have like 2 proof systems. And they also have this called round optimal one-sided statistical explainable 2PC. And they basically build all of these 4 primitives from 2-round SSPOT. So the proof systems are built from this 2-round statistically hiding commitment, and this round optimal statistical explainable 2PC is built from 3 primitives which are instantiated from 2-round SSPOT. And ultimately, you can see like everything is built from this 2-round SSPOT, which they instantiate from a variety of decisional assumptions. So let us focus on this 2-round SSP CDS. So what we do is we show that you don't need a 2-round SSP CDS. Rather, you can work with a 4-round SSP CDS, where the first 2 rounds are basically like pre-processing, or you can also call this as delayed input. And we show that you can build this the 4-round SSP CDS from our EOT. And you can also build the other primitives from this EOT and non-interactive commitment schemes. So essentially, we show that this 3-round SRP EOT and the non-interactive commitment scheme suffices to obtain the final result, this round optimal one-sided secure 2PC. And to talk about instantiations, we built this 3-round EOT from the 2-round SSPOT. And we also show, you can also build non-interactive commitment scheme from 2-round SSPOT. This re-obtains the result of KM20. But we also obtain new instantiation from CDH and reciprocal C side by constructing EOT and non-interactive commitment scheme from this. So let's see this CDS protocol a little bit. So this is what is a SSP CDS? So in an SSP conditional disclosure secrets for a language L, the sender has an NP statement X and a private message M, and the receiver has an NP statement X and a witness W. So in the protocol, the sender sends X comma M, the receiver sends X comma W, and the protocol sends M prime to receiver. So correctness says that M prime should be M if X and W is in the language. And the CDS protocol should satisfy computational receiver privacy. That is, the witness W is hidden from the computationally bounded sender. And the statistical sender privacy says that if the statement is not in the language, that is X comma W is not in the language for for all W, then the sender's private message is hidden from the receiver. So it's like the receiver is able to decrypt the sender's message from the CDS protocol messages only if it knows a valid witness. So let's briefly see how the construction of CDS protocol, SSP CDS protocol happens in KM20. So they basically construct this protocol from 2-round SSPOT and information theoretic garbling. So in the first round of the CDS protocol, the receiver invokes the SSPOT with choice bits as the witness bits. Then the sender basically garbles a circuit which has M, the private message M, hard-coded inside it, and the NP statement X. So this garble circuit takes as input the witness, and it verifies the X comma W, whether X and W is in the language. If it is, then it outputs M, else it outputs 0. And it also encrypts the wire labels for the witness inside the OT sender message as a OT sender message. So the sender sends this CDS2, which consists of the SSP OT sender message and the garble circuit to the receiver. Now the receiver obtains the wire labels corresponding to the witness, and then it evaluates the garble circuit to obtain the message M. So the garble circuit has to be information theoretic, and these are SSP. So that's why this is secure against a statistical receiver. So in our paper, we show that you don't really need 2 rounds. You can also work with a 4-round CDS. So in this, so in our paper, we define this 4-round CDS protocol where CDS1 and CDS2 are independent of the inputs X, M, and W. And the receiver here is statistical, while the sender is computationally bounded. So our protocol is kind of similar to the KM20 protocol. We just replace the 2-round SSPOT with our 4-round SSPOT in which is delayed input. So if you see the structure, it's exactly same. So that's how we construct our 4-round SSPOT protocol. So this kind of allows us to get new instantiations of SSP conditional disclosure of secrets from CDH and reciprocal C site. So to summarize, we build the round optimal one-sided statistically secure 2PC from these 2 ingredients. These are our ingredients. And we instantiate them from CDH and reciprocal C side. And we also instantiate them from the previous decisional assumptions. And this is the KM20 result. So to conclude, we obtained a round optimal one-sided secure 2PC from most concrete assumptions. We also proposed a delayed input SSP CDS, which has a pre-processing stage. And to conclude with some open questions, it would be interesting to study the round optimality of one-sided statistical 2PC, where you only use black box, where you only have black box usage of cryptographic primitives. And finally, one more interesting open question is to extend our result in the multi-party setting, where at least one of the parties is computationally unbounded. So thank you.
Thank you. Questions?
Could you clarify the modeling for the unbounded receiver in this delayed input CDS thing? Are you split staging the
In the CDS?
Yeah.
Yeah. So here this the receiver is statistically like it's unbounded. So and malicious, like both. Yeah.
But if it were unbounded without the witness, it could compute. So
it can compute the CDS1 and CDS2 message even without the witness. So if you see the protocol, it doesn't depend on the inputs. So the first and second round message is like pre-processing. So yeah, it only depends on the security parameter.
I see. Thanks.
Let's thank Pratik once again.
Thank you.
Okay, so we have the last talk of the day on perfectly secure 2-party computation for symmetric functionalities with correlated randomness. The talk would be given by Baralon.
Okay, so thank you. And today I'm going to talk about perfectly secure 2-party computation with correlated randomness. And this is joint work with Olga Nissenbaum, Aran Omri, Anat Paskin-Cherniavsky, and Arpita Patra. Okay, so in this work, we consider secure 2-party computation. Here we have 2 parties, Homer and Marge, each holding his own input. They interact in some protocol until they obtain an output. And we want this protocol to be secure. Specifically in our work, we consider perfect security. And to define it, we compare the real world to an idealized version of the computation where the parties have access to a trusted party that does the computation for them. So they send the trusted party their inputs and receive an output. And we said that the protocol is perfectly secure if for any adversary corrupting one of the parties in the real world, there exists a simulator corrupting one of the same party in the ideal world such that the 2 worlds are identically distributed. So this seems like a very strong definitions. We don't have an honest majority, we require perfect security. So we consider an augmentation of the real world where the parties have access to have access to the correlated randomness. So here, before the parties receive their inputs, they receive correlated randomness R1 and R2 that are correlated in some way that are completely independent of their inputs, but may depend on the function. After they receive the randomness, the parties receive their inputs, then they interact in some way and obtain an output. So this is the model that we consider, and we want to figure out which functionalities can be computed with perfect security given some correlated randomness. Let me talk about some previous results. So if we had in the multi-party setting, if there was a lot of honest parties, specifically more than 2/3 of the parties are honest, then classical results of BJW and CCD shows that everything can be computed with perfect security. And this even holds in the plain model without correlated randomness. And in the two parties, we have the result by Shai, Kushilevich, Melgard, Orlandi, and Paskin-Cherniavsky, and they showed the two results. The first result shows that if only one of the parties is supposed to receive the output, then any functionality can be computed given the appropriate correlated randomness. However, if both parties are supposed to receive the output, then XOR cannot be computed regardless of the correlation that they have. And in fact, their impossibility even rules out the weaker security notion called security with abort, where the adversary may abort, we allow it to abort and prevent the honest party from receiving the output. So this is what was known. So let me talk about what we do in this work. We have two main results. The first result is a complete characterization of which symmetric functionalities with up to 4 outputs can be computed with perfect security. And in fact, the positive results hold without correlated randomness, and our negative results, similarly to the Shai et al. Result, holds regardless of the correlation, and it rules out security with abort. So now I want to talk about which functions can be computed. So I'm going to view a function as a matrix where one party chooses a row, the other party chooses a column. So the first class of functionalities that can be computed is the trivial one, where only one party can affect the output. The second class is what we call spiral functionalities, and the reason we call them spiral is because they have this nice spiral structure inside their matrix. And finally, we have the function that is given by this matrix, which we call transparent transfer. And the reason for this naming is because it can be defined very similarly to oblivious transfer. However, here the choice bit of the receiver is revealed to the sender. So we show that only these 3 types of functions can be computed with perfect security. Our second result, we show that if a function contains an embedded XOR or an embedded AND, then it cannot be computed with perfect security. And this holds regardless of the number of outputs. And just to exemplify what an embedded AND and XOR means, it just means that we can find 2 rows and 2 columns such that the 4 outputs correspond to an XOR or an AND. Okay, so now I want to talk about the impossibility. Before going to our impossibility, as a warm-up, I'm going to talk about Shai et al. Proof of impossibility of XOR. So let's assume towards contradiction that there exists a protocol computing it. And let's consider an execution where the inputs of both parties are sampled uniformly at random. So the main observation in the proof is to notice that there exists this first round where Homer knows the output, regardless of the inputs X and Y, and regardless of the randomness R1 and R2. And the reason there exists this round is because the last round is an example of such round, so there must exist this first time where this happens. And similarly, there exists this first round where Marge knows the output regardless of all the inputs and randomness. And let's assume that Homer learns first for this case. So how do we define the attacker? So he will play honestly according to the specifications of the protocol until he learns the output. And this is where we use the fact that this is perfect security and not computational, because Homer can actually know that he knows the output. And the reason is that because we're dealing with perfect security, there is no security parameter. The real and ideal world are identically distributed. So we can just go over all possible honest continuations of the protocol and figure out the output to see if all of possible outputs are the same. So what it does with this information, if the output is to his liking, say he wants 0, then he will send the real message and they continue to play honestly until the end. And if he sees that the output is 1, then he will send only random messages. So why does this work? Well, intuitively, Marge still doesn't know the output for some choice of Y and R2, so there exists some probability that she haven't learned the output yet. This means that if the output is supposed to be 1, then there exists a continuation that will cause it to output 0. And because Homer sends messages that are completely random, this means that there exists some non-zero probability of increasing the chance of Marge outputting 0. So overall, when we do the computation, we can see that Marge outputs 0 probability that is slightly more than 1/2. And when we compare it to the ideal world, we can see that there is no simulator for this attacker because the output in the ideal world is just a uniform random bit. All right, so why does this fail for AND? Why can't we just simply take this and apply it for any other function? So as an example, let's consider AND. If we do exactly the same computation in the real world, we can see that Marge will output 0 with probability that is slightly more than 3/4. However, in the ideal world, the malicious simulator can change its input. So this means that he might be able to send 0 with certain probabilities such that the output in the ideal world will be 0 with exactly the same probability as in the ideal world. He can just increase the probability of 0. And considering the same with the same argument with an adversary that tries to bias towards 1, we can also do the same argument and see that there might exist a simulator. So this completely fails, so we need something else. What we do is make the following observation, and it's that sending 0 in the ideal world reveals no information to the simulator. So this suggests that we should also let the adversary to try and guess the input of the other party. And indeed, when we do the computation this time, we can see that the output of Marge is 0 and the adversary successfully guessed their input. The probability of this happening is slightly more than 1/2. And on the other hand, in the ideal world, sending 0 reveals no information, so the adversary will guess with probability at most 1/2, and sending 1 will cause the output to be a uniform random bit. So overall, no simulator will be able to go past 1/2 in the ideal world. And we use this idea in order to generalize this to other functions, but I won't go into all the details, but generally we consider the parties using inputs that are chosen uniformly at random from some subsets of their domains. And we consider adversaries that try to bias towards a subset of the output Z prime. So if he sees that the output is supposed to be in Z prime, he will continue to play honestly from that special one from before. And otherwise, he will send completely random messages. And we use this attack, and we then identify when this attack actually works, because it doesn't work all the time, and figure out when there exists this subset X prime, Y prime, and Z prime, such that the attacker actually works. So to summarize, we consider perfect security for two parties with correlated randomness. We gave a complete characterization for functionalities with up to 4 outputs. All of our negative results came from a more general impossibility, from which we also got our embedded XOR and embedded AND to be impossible to compute with perfect security. I haven't talked about it, but just like Ishai et al., our negative results rules out security with a bot. And we also showed that there are some interesting functions that can be computed with perfect security, and in fact, our positive result holds even in the plane model without correlated randomness. And that's it. Thank you.
Thank you. Does anyone have questions?
Thanks for the talk. So this seems pretty similar to all this work on like for which functionalities can you get fairness even with the dishonest majority setting, right? You have, I don't know if you're familiar with these works, that if you have an embedded XOR, you can also not achieve fairness and so on.
So yeah, there are this, so you're talking about the computational setting.
Mm-hmm.
So in the computational setting, it's a bit different because in the computational setting, the adversary doesn't necessarily know that he knows the output. Here we use the fact that in perfect security, he can know that.
Okay.
So it's slightly different.
Okay. Could you provide, I mean, I maybe missed this, but why the limitation on 4 outputs?
Because when we try to identify when this attack works, it turns out to be much harder to analyze for more than 4 outputs.
Yeah, thank you.
Any other questions? I just had a quick one about the corruption model. Like, is it adaptive corruption or?
No, just 2-party, 1 corruption.
Oh, okay, I think. All right, yeah. If not, let's thank VAR and all the speakers of the session.